All right, guys, we're going to continue with confidence intervals, and we're going to look at creating confidence intervals for proportions. So now we're really getting into the heart of inferential statistics and how we actually go about creating these confidence intervals. So, first saying, what are the three conditions for constructing a confidence interval for a proportion? And what happens if one of those conditions are violated? So you're going to see that a lot of this stuff is similar to what we saw in the last chapter based on sampling distributions and those conditions that applied there. We're going to see those conditions hold through from now until the end of the course. So the first condition that we need to deal with when we're talking about a condition for creating a confidence interval for a proportion is the condition of randomness. And that condition of randomness is telling us that our data must be from a random sample or a randomized experiment, meaning that random assignment is has occurred. Okay, you must specify and be specific about whether it is a random sample or it's random assignment. The reason that we care about that idea or concept of a random sample or random assignment is when we're using a confidence interval, we're collecting sample data and we're trying to use that sample data to make an inference, either to generalize those results to the broader population if we've taken a random sample, or to show some type of cause and effect relationship in the case of random assignment. So condition number one that we need to check is our condition of randomness. Our second condition, which you hopefully have remembered, is our large counts condition, which tells us that the sampling distribution is approximately normal. Our large counts condition or our normality condition for proportion problems is n times p hat is greater than or equal to 10, and n times 1 minus p hat is greater than or equal to 10. Notice that we're using a p hat value here as opposed to p, which we might have used in the previous chapter, because we don't know what p is. We're trying to estimate p, so we have to use p hat. As usual, we have to show these values in our calculations and actually show that work out. Finally, we have our independence condition amongst our samples, which is our 10% condition. That just means that our sample size of n must be less than or equal to 1/10 or 10% of the population size. These conditions are something that you need to memorize. When you see proportion problems, you need to know I'm checking my randomness condition, I'm checking my large counts / normality condition, and then I'm checking my independence condition. Must be checked on every single confidence interval problem for a proportion. Some vocabulary and something for you to know is the difference between the standard deviation of a statistic and the standard error of a statistic. It's very rare and unrealistic that we would know the standard deviation of the statistic. That would be in the case where we'd actually know what P, our population proportion, is. It's very rare that you would know what your population proportion is. We generally don't have the standard deviation of the statistic. Instead, we have the standard error of the statistic, which uses p hat as opposed to p in that formula. This is on the formula sheet. If we go ahead and we take a look, you'll see the standard error of the statistic versus the parameter, and you'll see the only difference is using p hat as opposed to p. As I said, this formula is on the formula sheet, and the standard error of the statistic, or the standard error in this case of the sample proportion most specifically, describes how close the sample proportion of p hat will typically be from the true population proportion in repeated simple random samples of size n. So what that standard error is measuring is how far on average you are going to be away from the actual proportion. So for example, maybe the actual proportion of people in the US who own a dog is 30%. And we find the standard error of our sample statistic to be 0.10. That means on average, when we go out and we take a sample and we get a p hat, it's going to be 0.1 away from that population proportion of 0.3. So it's how far on average you are in your samples away from the actual value. When we are creating a confidence interval, and again, you'll see that formula very generally on the formula sheet right here, statistic plus or minus critical value times the standard error of the statistic. Well, we just talked about what the standard error of the statistic is. Now we have to kind of think about what this idea of a critical value is. So when we're creating a confidence interval, okay, like I said, we have the statistic plus or minus the critical value times the standard error of the statistic. Most specifically, if for a proportion problem, that's going to look like p hat plus or minus z star. Z star is what's referred to as your critical value times, and then there's our formula for the standard error of the statistic. In order to find that z star value, we could use the standard normal table, and actually we're going to use table B, which is our table for t critical values, but I'll show you how to use that to find that value. Or you can also use inverse norm on the calculator. What that critical value tells you or measures is how many standard errors we need to extend above and below to reach the desired confidence level. So how far away we want to be from that mean, okay, to reach the desired confidence level that we want to reach. The higher your confidence level, the higher your critical value is going to be. So how do we find a critical value? Well, we're going to talk about that in class, but the easiest way to find z star critical values is not to use the standard normal table, which you could use, but actually to go down and to a new table called table B. Table B is mostly used for t critical values, except for the bottom row, which you're going to see right here. The infinity row of the t distribution is really where your z critical values lie. And notice you have the confidence levels down in here that correspond with those critical values. So in order to find a critical value for z, for example, the 90% critical value, I would just go to 90% and then the infinity row, and I would get my critical value of 1.645. You could also use this inverse norm on your calculator. If you wanted to do that, it becomes a little bit more tricky depending on if you have a newer calculator or not. For example, if I had a newer calculator, life becomes easier because you can change the tail to center. And you would get that same value of 1.645 that we got on the using the table. If I don't have a newer calculator, I only can do a left tail, which makes it a little bit more challenging to use inverse norm. So my suggestion is if you have a newer calculator where you can change it to center, then you can go ahead and use that to find your critical values. If not, it's really easy to just look them up in the table on your t distribution table in the infinity row to get the correct critical value. Heading back to the notes, okay? What is the formula for a one sample z interval for a proportion? That is the fancy name for it. And as we said, it's just your p hat plus or minus your z star times your standard error, which is p hat times 1 minus p hat over n underneath the square root. This formula is not officially on the formula sheet. Keep in mind, when you are doing a problem, you must always check the conditions, which are your randomness condition, your large counts condition, and your independence condition. We'll look at the next example in class. When we are creating this confidence interval, our book likes to use a 4-step process, which is pretty helpful in actually organizing your steps. So it's not a bad idea to do this. Step 1, your state, plan, do, and conclude. Those are your 4 steps. Step 1 is state the parameter you want to estimate and the confidence level. I'm trying to estimate the proportion of all people in the US who own a dog at a 95% confidence level. Step 2 is your plan. Check your conditions, identify and name the inference method. We're going to be seeing lots and lots and lots of different inference methods from now until the end of the year. It's important that you get the name correctly down. Step 3, do. Actually perform your calculations out. Step 4, conclude. Interpret your results in the context of the problem. That's where we get to our point. We are blank % confident that the interval from blank to blank captures the whatever we're talking about. Can you use the calculator? You absolutely can use the calculator to do these. On the calculator, it will do all the hard work for you, all the calculations. If you go to stat and over to tests, there's lots of different tests. From now until the end of the year, this is what we're doing. You are doing in this particular section a one prop z interval, a one proportion z interval, or a z interval for a one sample proportion. If you are going, you would hit enter, by the way, and then you'd enter in the information, which we'll see in class. If you are going to use the calculator, there is no opportunity for partial credit, and you must name the interval or the test that you are doing. So it's not a bad idea to use the calculator, but keep in mind you must name the interval that you are using. We'll look at the next example in class. Let's move on and talk about margin of error and how we measure margin of error. So when we're measuring margin of error, the margin of error is just that second half of our formula. It's the z star times the square root of p hat times 1 minus p hat over n. It's that section of our confidence interval. Lots of times you're going to be asked a question on almost every AP exam. It's either a multiple choice or a free response, where you'll be asked to solve for the minimum sample size given a certain margin of error. Sometimes in those problems, they don't give you a p hat to use. If they give you one, then use it. If they don't, we always use the most conservative estimate for p hat, which is 0.5, which would lead to the largest possible sample size that you can get. You'll see what I'm talking about when we look at the next example there. So those are the basics for this particular lesson. Really interesting stuff, really important stuff. We're going to look at lots and lots of examples. We'll collect our own data on certain things, and I'll see you in class for confidence intervals for proportions.